Welcome back. Today we're going to continue with our extensive discussion of arithmetic expressions, a syntax and a semantics for arithmetic expressions, including an automated evaluator that can take any arithmetic expression and reduce it to its meaning as a natural number. So as usual, our agenda is pretty simple, and here it is. I'm going to summarize where we've been and then where we're going today and why we're going there today in order to set up for the near-term future of this class. So 2 lectures ago, we defined a very simple language, an extremely simple language. It had just 4 terms, 4 expressions, if you want to think of them as expressions, these variable objects. They were objects X, Y, Z, and W, we named them, of a type we called variable or var, I forget what the details were. And we defined various interpretation functions that took values of this syntactic type, this variable type. In other words, a function that could take either X or Y or Z or W as an argument, and that would return a corresponding value for that object. We saw that we could define interpretations that took variables and returned natural numbers. And we saw that we could define interpretations that took variables and returned other types of objects. And in particular, we looked at returning Boolean values for each of those variables. Even if we have settled on just one type of return value, of course, there are many, many different interpretations that we can return. If we map if our interpretation functions map these variable objects to natural numbers y, there's an infinity of possible interpretations, right? So x could go to 0, y, z, and w could all go to 0, or x could go to 1, y, z, and w could go to 0, or x could go to 2, y, z, and w could go to 0, or x could go to 2, and y could go to 1, and z could go to 3, and w could go to 1117. You get the idea. There's an infinity of possible interpretations if the domain of discourse is the natural numbers. It's not actually true if the domain to which we map these variable objects is Booleans, right? There's only 2 possible ways to map x to a Boolean value. X either goes to true or x maps to false. So there's only 2 possibilities with one variable. If we have 2 variables, x and y, for each possible value of x, there's 2 possible values of y, so there's 2 possible values for x. For each of those, there's 2 possible values for y. So now there's only 4 possible combinations of, there's only 4 possible interpretations, really, for 2 variables whose interpretations take them to the domain of Boolean values. So that's going to turn out to be really important. There's a finite number of functions from a finite number of variables to Boolean values. We'll talk more about that as we go forward. Okay, so to summarize, we defined a syntax in the form of a set of 4 terms, just little variable terms. We defined interpretation functions that associate each term with a corresponding value. And finally, we wrote an evaluation function that takes as its arguments a term, a variable like x or y or z or w, and an interpretation function that, given any term, returns its value in the corresponding semantic domain, and where this evaluation function then returns the value of the semantic value of the given term, and it does it by just applying the interpretation function to that term and returning the result of evaluating that application expression in lean. Okay? So if what I just said didn't make enough sense to you, stop here and go back to the previous, to 2 lectures ago, and please review what we did there. You should have transcribed all of the contents of that lecture into a set of definitions in a lean file that you have in your main project now. So go back and review what we did, and then come back here and continue forward. Right? So 2 lectures ago, we defined this little tiny language. Last lecture, we spent a lot of time looking at inductive definitions of various kinds of trees. And we saw lots of commonality. A binary tree is sort of a binary tree is a binary tree, and they mainly vary in the types of contents that you can store in the nodes. So by the end of the last lecture, we saw that we could define an inductive data type that kind of captured the notion of what it means to be a binary tree in a polymorphic way. Okay, and we saw that we could define recursive functions that would do case analysis on a given tree, see if it was either empty or non-empty, and then compute and return some value depending on which of those cases we're looking at. So if we wanted to compute the size of a tree, for example, well, we'd have two cases. If the tree is empty, return 0. If the tree is not empty, add 1 for the top level node in the tree, and then recursively compute the sizes of the two subtrees. Add all those three figures together, and now you have the size of the overall tree. Again, if that doesn't make sense to you, stop the video here, go back and look what you did in the last lecture, review your notes, do some more experiments, make sure you've wrapped your head around these ideas, and then you'll be set up for today. So today we're going to combine these ideas to make a great leap into the future of the class. Okay, we're going to combine these ideas to define a language of arithmetic expressions. Now, some number of lectures ago, we talked about how languages like various logics generally have three kinds of expressions. They have literal expressions that kind of literally represent certain values. They have variable expressions that, as long as you have an interpretation that tells you what the variables mean, associates variables with meanings. And then you have application expressions where some kind of operator or function is applied to one or more smaller expressions in order to combine them into a bigger expression. So if we have this sum of values over here and this sum of values over here, and now we can combine those into an even bigger expression by connecting them with, say, an AND operator expression. So we'd have addition, for example. The addition of this expression and this expression is a larger expression. Now, to compute the meaning of that larger expression, we do it in a way that we call compositionally. We compute a meaning for one sub-expression, we compute a meaning for the other sub-expression, and we combine those meanings with, in some particular way to compute a meaning for the overall tree. And so today we're going to see how to formalize in Lean, how to formally specify a language of arithmetic expressions, okay, as a tree of smaller expressions. And that's how programming languages are defined. We're going to build a simple programming language, one in which you can write arithmetic expressions of arbitrary complexity, along with the concept of interpretations and an evaluation function that can take any expression and reduce it to its meaning as a natural number. Today's lecture is preparation for a very near future transition where we'll go even simpler and we'll look at a language of Boolean expressions. Okay, and in Boolean expressions, we don't have plus and times and minus applied to expressions that mean natural numbers. We have Boolean operators like and or and not applied to smaller expressions that mean Boolean values. Okay, so that's where we're going. So today is bullet number 3. We're going to build, for the first time, an actually useful and interesting little programming language. It's not a complete programming language. It doesn't allow you to do loops and things like that. But it certainly allows you to write interesting expressions of arbitrary sizes and to compute their values. Okay, so that's where we're going. So let's head on over to VS Code and we'll get started there. Cool. Here we are back in VS Code, and we're in the state in VS Code where we left it at the end of part 1 of this lecture. So I'm going to go ahead and close out the files that we're looking at here, trees.lean and treetest.lean, and I'll save the changes to these files. I'll bring up my project browser, Control B on my Windows machine, Command B on your machine. Here's our Scratch directory, here's our old directory. And today we're going to build such an important and interesting and useful little file. I think that we'll build it just right straight in the source directory rather than putting it in one of these other subdirectories. So let's create a new file in the source directory called, how about exp.lean. And that will be short for arithmetic expression.lean. Okay, so take a minute and get yourself started. I'm going to hit Control S here, Command S to save this file. I've now saved an empty file and I'm ready to get working. So we have, our goal here is to produce a language of arithmetic expressions that supports three kinds of expressions. They will be literal expression, variable expressions, and operator or operator application expressions. And these are just the kinds of expressions we've been talking about all along. So an example of a literal expression, without getting into the syntax that we'll use in Lean, would be, just 2 or 5 or 3 or 4. A variable expression might be something like x or y or z or w. Or maybe we'll give different names to our variables here. We'll call them v_0, v_1, v_2, and so on and so forth. And finally, operator expressions. And we'll start with what we call binary operators. And binary operators are functions. That's all they really represent. Operators that take two arguments and combine them together. So, it's a fancy word, operator, but it just means things like the plus operator in arithmetic, or the times or minus or divide, or so on and so forth. A binary operator takes two arguments, so plus, for example, or addition, takes two values, adds them together, and yields a new value. Unary operators just take one argument, and a good example of a unary operator in arithmetic is the factorial operator, right? So if you have 5, you can say 5 factorial, typically denoted with an exclamation point. That's a unary operator that takes just one argument, the 5, and that then computes a result, or designates or denotes a result, 5 factorial, which is, of course, just 5 times 4 factorial. Oh yeah, hey, that's cool. That's kind of a recursive way to think about factorial function, right? So wait, you're telling me that n factorial is n times n minus 1 factorial? Sure, of course it is. Okay, so that's an aside to kind of get your brain warmed up a little bit for, where we might do a little bit of homework at some point, but we're not there yet. So the operators that we'll implement will be, plus, minus, and times. How about that? Or maybe just a subset of them. Good. And so given that syntax, then we ought to be able to write expressions like, and I'm not going to write them again the way that we're going to have to format them in Lean, but things like 4 plus x times y. Okay, so here is a binary operator. You have its two arguments on its left and right. We're using infix notation here, where the arguments, where the operators place between the arguments. And so we have an operator, times, combining two smaller arithmetic expressions into one bigger arithmetic expression. To evaluate this, we're going to have to evaluate what the term on the left means, 4 plus x. And that, of course, is just a smaller operator expression. So to evaluate that, we're going to have to evaluate what literal 4 means, and that just means the number 4. And we're going to have to evaluate what the variable x means, and for that, we're going to need to have an interpretation function that takes variables and returns what they mean under some interpretation or other. To evaluate the right-hand side, well, that's a variable expression, so we'll need to evaluate that under an interpretation, the same one that we use on the left-hand side, by the way. We don't want the meanings of variables to change, as we're evaluating an expression. So we'll take an interpretation and figure out what y means. So now we have 4 plus x. This evaluates to 4. X may evaluate to 6, for example. The plus operator evaluates to the addition function. Okay? This plus operator is a piece of syntax, but what it means is the addition function from, like, arithmetic. Okay? So given that this literal 4 evaluates to the number 4, given that x evaluates to 6 under some interpretation, given that plus evaluates to the addition function, this ends up evaluating to 10. We take that, we evaluate the right-hand side, apply an interpretation function to y, maybe it means 5, and evaluate now the operator expression here. The operator, the star, means arithmetic multiplication, so now we have 10 here, we have 5 here, we have an operator that means multiplication, so we look up the definition of multiplication, we apply that function to 10 and to 5, and we get 50. Okay, so that's basically the idea. If I said all of that too fast, stop the video here and rewind it and go back and think about it again. Okay, now what does this have to do with trees? Well, really you can think about this expression as an expression tree. So times is an operator at the top. Let me just use, characters on the keyboard. We have two sub-expressions, right? On the left, we have this expression 4 plus x here, and I will just plug it in. Let me make some space here, like that. On the right, we have the expression y. Let me put it in like that. This expression really is a smaller tree, right? So, whoops, we have here, we really have the plus operator at the top of the tree, and it has two children. Sorry, I'm messing around here. It has two children, and so let me draw them in like this and like that. And those children are, of course, 4. So we'll put the 4 here, and the x here. We'll do our drawing a little bit more carefully, like that. No longer need that. And there is our expression tree. To evaluate what this overall tree means, what do? Well, we look up the meaning of that, and that means multiplication. We evaluate the left subtree. That's going to mean 10 in the example that we just went through. We evaluate the right subtree. That's going to mean 5 in the example that we just went through. So we have 10, the natural number here, represented by a nat in lean. We have 5 represented by a nat in lean. We map this operator symbol to a function for, in this case, natural number multiplication. Then we multiply the 10 here by the 5 here and get 50, and thereby we reduce that big expression tree to a natural number. One of the things that I have elided in this tree are the empty subtrees below the, we'll actually come to that. We're not actually going to need to have empty subtrees. We'll just take variable trees and literal trees as sort of the kinds of leaves in arithmetic expression trees. Okay, so good. So that's meant to give you an intuitive sense of where we're going, and a sense of how expressions can be understood as trees, and how evaluation of such trees can be done recursively. To evaluate, let's think about that just a little bit more. To evaluate this big tree, we have an evaluation function that takes an interpretation for the variables, and one of these trees is its arguments. What does it do? It evaluates the left subtree given, let's think. If it's a literal tree, it just evaluates the literal and should return 4. If it's just a variable tree, a variable expression, it will apply an interpretation function to that variable to compute its value, and that's the value of the tree. If it's an operator tree, then it's an operator at the top with 2 subtrees, and that's where the recursion comes in. To evaluate that kind of tree, we evaluate the left subtree to get a number recursively. We evaluate the right subtree recursively to get a number. We figure out what the operator means arithmetically, what function does it represent, and then we apply that function to the values of the left and right subtrees, and that reduces the overall tree to its meaning as a natural number. Okay, so the idea then is we're going to define an inductive data type, just like we did before, to represent the syntax, the possible forms of arithmetic expression trees. We're going to define interpretation functions just like we did before to map variables to their values so that we can interpret variable expressions. And we're going to build a recursive evaluator that, given any expression tree and an interpretation, applies case analysis to figure out what kind of tree you have and returns a result accordingly. For a literal expression, we'll just return what it literally means, and we'll see how to do that in just a few minutes. For a variable expression, we'll apply the given interpretation function to that variable to get its value and return that. And for an operator expression, we'll look up what the operator means and we'll recursively evaluate the left and right subtrees to get values to which we can apply the right arithmetic function to produce an answer, which will be the result of that tree. And in this way, in just a few lines of code, we will have built the capability, a possibility of building arbitrarily complex, arbitrarily large, arbitrarily deeply nested arithmetic expressions, and a capability to evaluate them automatically to reduce any such tree, any such expression to its meaning as a natural number. So in other words, we're going to kind of build a calculator where we can program the calculator by programming in an expression to be evaluated and having the machine then reduce that expression tree to its semantic meaning. So once again, we're building a language. A language has a syntax, the set of all possible expressions in the language, and a semantics, which to each possible expression in the language, of which there can be an infinite number, a semantics will assign a corresponding meaning in a semantic domain, here the domain of natural numbers. Cool, right? So let's get started. The first thing that we're going to need, the first piece of this puzzle that we're going to put together has to do with variables. And you should be very familiar with this idea. Once again, I am going to limit the number of variables that we can use in our arithmetic expressions to 4. It's easy to generalize this to handle any number of possible variables, but it just makes the presentation a little bit more complicated and doesn't really give you any more insight into what's really going on. So let's do as we did before and just define a data type to represent variables. Okay, and instead of calling them x, y, z, and w, I'm going to call them v sub 0, v sub 1, v sub 2, and v sub 3. So here's how you do it. Inductive, and we'll use var to be the name of our variable type. And I'm just going to enumerate the variables that will be available to us, and I'm going to call them v sub, and I'm going to read that underscore as sub, v sub 0, and v sub 1, and v sub 2, and v sub 3. Okay, so those will be the 4 variables that we have to work with. Now, Lean infers that the types of these constant terms. There's no arguments that allow you to make variations on the v0 term. It's just a constant. Lean knows that that's of type var, but I'm going to go ahead and add the explicit type declaration anyway, just so that you're reminded what the types of these objects are when you go back and look at this definition shortly. Okay. Now, the next piece of the syntax that we're going to address is the need to represent operators. And for now, we'll just stick with binary operators, and let's just go with 2 of them. Let's define a language with addition and multiplication operators. Now remember, this has to do with the syntax of our language. It's just the kind of symbol that can appear in an expression. And we'll call, and so once again, we're just going to define a data type for the possible syntactic operator expressions. Because these are binary operators, I'm going to call our data type binop, or binary for binary operator. Okay, and just as before, I'm just going to enumerate the possible values, and let's call one of our operators add, and that's of type binop, and let's call the other operator mul, and that's also of type binop. Okay, so there we have our the variables that we can incorporate into expressions in our language. And you'll see what I mean by that. I said that carefully. There's a tiny little complication there, but it's essential, and we'll get there shortly. So we've defined the variables that we can use, that we can incorporate into variable expressions in our language, and we've defined the two binary operators that we'll be able to use, at least in the first version of our language. It would be easy to add subtraction and other operators, and I'll have you do that as part of your homework. Okay, so now we need to get to the notion of interpretations. We saw in a couple of lectures ago that there are many different interpretations that we can give even to a set of 4 variables. In this lecture, we're talking about arithmetic expressions, and so an interpretation will necessarily map in our language each of these variable objects to a corresponding natural number. Okay, so let me just make a comment there. An interpretation for variables will map each variable v sub 0, v sub 1, v sub 2, or v sub 3 to a corresponding natural number. That's how we think about the domain, represented as a value of type nat in the environment that we're using here. I'm not actually going to define any interpretations right here, but I'd ask you to stop right now. Actually, I'll do it with you, okay? Let's define just one interpretation. Let's call it, var, let's call it the interp 0. So we'll define interp 0 to be an interpretation that, given any var object, returns a value of type nat. Okay. And we will use wildcard here to match any possible variable, and given any variable, we'll always return 0. Okay, so you should have been able to do that yourself, but if you forgot, there's an example of an interpretation for variables. You can, of course, define many interpretations for variables, and so this really belongs in a related test file, because it's not essential to the definitions we're giving here. So let's actually create a new file in our source file called exp_test.lean, and let's put this code right in there. Okay, I paste it in, and of course, var is not defined in this file. I need to import the definitions from exp.lean. So I can import from the current directory exp. I leave off the .lean. And now, having incorporated all of the definitions from exp.lean into exp.test.lean, var is now defined in this file. Okay, so let's see, I'm going to divide my screen in half by going to View, Editor Layout, Split Right, and I'd like, I'm going to drag this test tab over here. So I have my test file over here. I have my main file here. I'm going to close out the project browser. Good. Good. So here's my definition of variables. This gives me a sense of an interpretation for variables. Many other interpretations are possible. Okay, good. And if I wanted to, of course, I could eval interp 0 applied to any of my variables, like v_1. v_1 is undefined. It's because I haven't opened the namespace var, and I don't want to for reasons that you might see later. So I'll just say var.v1, and of course, under this interpretation, interp 0, v1 is bound to the value 0. So if I hover over this, then there's the 0 right there. Good. That should all be review. Okay. The only thing we've done here is use different names for our variables. Instead of calling them x, y, z, and w, I've called them v_1, v_2, v_3, and so on and so forth. Good. We've also defined a data type for are binary operators. So we're really using multiple inductive data types to define various elements of the syntax of our language. Now, whereas the interpretations that we apply to variables will differ depending on what we want variables to mean, we're always going to want our binary operators to mean the same thing. So this binary operator add, for example, should really always be interpreted as meaning the natural number addition function. And this operator, which goes into the syntax of our expressions, should always be interpreted as meaning the natural number multiplication operator. So we're going to define in our main file an interpretation for binary operators, and it will never change. So I'm going to define binop interp as a function that, given any binary operator, returns, well, what? What does it return? It returns a binary function on natural numbers, like addition, the real natural number addition function, right? Let's go here, if I evaluate this expression in lean, 3 plus 4, that evaluates to 7. This is a binary operator symbol that lean interprets as meaning natural number addition. So when it evaluates this whole expression, it evaluates this literal, comes up with 3, evaluates this literal, comes up with 4, evaluates this symbol as meaning natural number addition. When you hover over this, you get something kind of complicated that you can ignore for now. And that means exactly the same, and in fact it reduces to nat.add 3, 4. So nat.add really is the name of the function that gets run when this expression gets evaluated. So what do we want the add binary operator to be interpreted as? Well, we want to interpret the add binary operator in our syntactic expressions as meaning this function here, nat.add. Okay, now, so we want more generally to take any binary operator, of which there's just 2 in our language so far, and to return the function that they are intended to mean. So we need to take any binary operator and return a value of what type? Well, what's the type of nat.add? If we just hover over nat.add here, we see that the type of nat.add is nat to nat to nat. It's a function that takes 2 natural numbers and returns a natural number as a result. You'll recall that it can actually be read as a function that takes 1 natural number and returns a function that takes the second natural number and returns a result. That's that concept of partial evaluation. But for our purposes here, it's just fine to think of it as a function that takes 2 natural numbers and returns a natural number as a result. So our binary operator interpretation function, binop interp, should take any binary operator and return a binary function on natural numbers. And any such function is going to be of that type, nat to nat to nat. Okay. So we're defining a function that takes a term in our language, the addition or multiplication binary operator, and returns a function of the right result, of the right type. In particular, if this function binop interp is applied to binop.add, this term right here, what do we want to return? Nat.add. We want to return this function right here. Okay? And if we interpret our mul binary operator, we want to interpret that symbolic expression in our language as a function in the domain of arithmetic, the function that multiplies 2 natural numbers. So if we apply our interpretation function to binop.mul, we want to return function nat.mul. That's the name of the function that does natural number multiplication. Very cool, right? Okay, let's just see an example. So I'm going to take these comments here, and put them over in the test file to keep our main file clean. And I'll put a little comment here, how arithmetic evaluation works in Lean, and what function does addition for natural numbers in Lean. Okay, that's this function here, nat.add. Good. Okay, and we can do a little test now with our binop interp. Let's evaluate not 3 plus 4 or nat add 3, 4. Let's take this. We'll put this expression in here, but we'll replace nat.add with binop interp applied to binop.add. Okay, look at this term here and figure out what it reduces to. When Lean evaluates this function application expression, binop interp, applied to binop.add, what's the result? Well, we look up the definition of binop interp, and that's here. We're given a binary operator as an argument, that's binop.add here. We do case analysis. If the argument is binop.add, which it is, then we return nat.add. So this entire expression reduces to the function nat.add, which then gets applied to 3 and 4 and does exactly the same thing that this expression up here did. If we applied binop interp to binop.mul, then of course this expression is going to reduce to nat.mul, and the result of applying the nat.mul function to 3 and 4 should be 12, and sure enough, it is, as we expected. Okay, great. So now we're set up to define the syntax of our expression language. We have all the pieces that we need to define what set of expression trees can be built in our arithmetic expression language. So you've seen quite a lot so far. I suggest you pause the video at this point, go take a breath of fresh air, or have another cup of hot chocolate or tea or coffee or whatever. Think about what we've talked about for just a couple of minutes, let it sink in, come back and look it over again very quickly to make sure that you're okay with it, and then hit play again, and we'll continue on. Okay, you're back, I'm back, and here we go forward. So now we'll define the syntax of our expression language. And we're going to define an expression language for arithmetic expressions in which there are 3 kinds of expressions: literal, variable, and operator expressions. Okay. So let's define a data type called AEXP, and that will be the type of expressions constituting the syntax of our language. So this is going to be a type, and there's going to be 3 ways to build an expression. There are going to be literal expressions, there are going to be variable expressions, and there are going to be application expressions. And I'm going to call these app2 because these are going to be expressions in which a binary operator is applied to 2 arguments. Okay, we're not going to have this notion of currying partial evaluation in our expression language. If you have a binary operator, you're going to have to provide 2 arguments to it for it to work. Okay, we'll come back and add app1 later for unary operators, and that'll probably be part of your homework. Okay, so how do we want to build a literal expression? What is a literal expression? Well, it's something like the expression for, and when we eventually evaluate that expression, that literal expression in our language, we want it to evaluate to the natural number 4. So the way that we're going to build a literal expression is with this constructor lit, but we're going to give it 1 argument, and that argument is just going to be the value that we want that expression to evaluate to. What type of object do we want one of our literal expressions to evaluate to? Well, a natural number. And so that's how we're going to build a literal expression. Okay. In fact, I'm going to stop right here and erase these other two expressions. And let's come on over and just see what this means. Let's see. So let's some expressions in our language. Okay. Let's define a literal expression. I'm going to call it L6, capital L6 for literal value 6. How would I build that expression? Well, it's going to be aexp.lit. That's this constructor, aexp.lit, applied to a value of type nat. And what value do I want literal 6 to evaluate to? Well, I want it to evaluate to 6. Okay. So you can actually think of this term as sort of like just this constructor name in front of this literal value 6, and that overall term is an expression in our language. And we've assigned that expression a simpler name here. We've just called it L6. But this term that I've highlighted in the browser, in the editor here, is exactly a term in our language as we've defined it so far. You go ahead and define a term, call it L5, that constitutes a literal expression for the value 5. F L5 colon equals. We want a literal expression in our arithmetic expression language, so it's ax.lit. And then we stick 5 in there. Okay? You can almost think of this as like a 5 in a box that's labeled lit, or ax.lit. Okay? Think of, actually it is this term all by itself. That is a term in our language as we've defined it. Okay? Now, we're also going to have variable expressions in our language. So we'll define a constructor called var. And I want to be clear that this constructor var here is not the same as this type var here. Okay, I'm using the same name in two different ways. And of course, this var is really ax.var, which is different than this var term up here. I could have used a different constructor name here, and maybe it would have been less confusing, but get used to it. It's not unusual that you have the same name used in different ways in the same set of definitions or in the same piece of code. Okay, so the idea here is that a variable expression is going to have as its argument one of our variable objects. Okay, and so it will take a value which is not going to be a natural number, but that's going to be one of our variable objects. And it might not be obvious immediately that you can use var here to represent a constructor for this type, and that if you use var here, it actually Lean understands that here var is a type, it's this type up here, but this works out just fine. So this var and this var are actually different. This is a constructor for this type. This is a type, the type of our variable objects, v0, v1, v2, and v3. Okay. So now we can come over here and we can define some variable expressions in our language. And here you'll see why I chose to change the names of variables in our variable type to v0, v1, v2, and v3, because what I want to do now is I want to define a variable expression in our arithmetic expression language. Actually, let's just do check here before I do anything. I want a variable expression, so that's going to be ax.var applied to an argument of the right type, like v sub 0. And I need to say var.v sub 0 because I haven't opened this data type. And now you see why I didn't open the var type, because I didn't want any kind of conflict involving these two different uses of the var keyword. So here's an expression in our language, the language that we're defining. It looks complicated and ugly. We can clean that up with some what we call syntactic sugar, but essentially this is the form of a variable expression in our language. Okay, and just as I assigned the value of a literal expression to a nice name L6 here, I can assign a variable expression to a nice identifier, and in this case I'm going to choose X. And there you go. Okay, so I've given a very nice simple name X, now not to a variable of type var, but to an arithmetic expression built using the var constructor. So X now in this file is not a variable, it's a variable expression. It's a value of the AX type, not of the var type. Although this arithmetic expression does incorporate as its first and only argument a variable object, in particular v0. Okay? So let's give nice names to y to the other four variables, v0, v1, v2, and v3. Here we have, well, we're trying to get to redefine x. That doesn't work. So we'll use different variable names here, z and w. Cool. Okay, so now we have two literal expressions, L5 and L6. We have four variable expressions that are in our language. And now all we need to do is define the syntax of application expressions. In particular here, we're going to have expressions for applying binary operators. So we'll call this constructor app2. And what are the arguments that this constructor should take? We want to be able to build larger expressions by applying binary operator expressions to smaller arithmetic expressions, which could themselves be literal, variable, or smaller operator expressions, recursively all the way down. Okay. If you're hearing funny noises here, it's because my cat is running around. So say hi to the cat. There you go. Okay. By the way, you can Google this. Did I tell you this already? Yeah, I probably did. If you're posting pictures on dating sites, don't include your cat. The science is clear. Doesn't help. Okay, sorry about that, but I found that to be curious, and you can Google it if you want to follow up on that. Okay, so what are the arguments that we want to apply to the app2 constructor to build an application expression, an operator expression, a binary operator expression, if you want to think of it as that? Well, we need an operator, which is of type binop, one of our binary operators, either binop.add or binop.mul, and two smaller arithmetic expressions. Okay, and we can call them left and right, and they're going to be of type AX. Okay, and there again is that circularity. But it's not an infinite circularity because you always have to provide smaller arithmetic expressions to build up larger arithmetic expressions. And terms in lean and in inductively defined types in general are always built up by some arbitrarily large but always finite number of applications of the available constructors. So if you've applied app2 a billion times, then you have a tree of expressions a billion deep, but that's still finite. And that means when you evaluate one of those trees recursively, eventually you're going to get down to literal or variable expressions, and the recursion will terminate. Okay, cool. Okay, so now let's go over into our test file and use our new capability to build larger expressions, arithmetic expressions. Let's define arithmetic expression. We'll call it A1. We could actually let's just do it within a check first. We want to build an arithmetic expression. So it's going to be ax.ap2. We could even put in underscores here, I believe. Yeah, Lean doesn't look at those at this point. Okay, so we need a binary. Well, maybe I need 3 of them. Still not okay. Yeah. Okay, so we need a binary operator expression. So that would be binop.add, for example. There's one of our binary operator expressions. So we will be building an addition expression here, and we need 2 smaller arithmetic expressions. So how about L6 and L5? Yeah, cool. Okay, why don't you take a minute and in a comment, and I'll do it in just a second, just stop the video and draw a little tree just using characters on your keyboard for this arithmetic expression here. Okay, we can do that. So it looks like this. Binop.add is the operator at the top of the tree, and then there's a left subtree and a right subtree. And below the left subtree, we have L6, and below the right subtree, we have L5. Okay, so that's the expression tree for the expression that we've built here with this piece of admittedly kind of ugly code, if you will, but it is what it is. Okay. Again, Lean provides some capabilities for cleaning this kind of code up with some notations that make it look a lot more like just ordinary arithmetic, but we're not there yet. Okay. That's pretty awesome, right? So let's assign this expression a name. We'll call it, I don't know, A1 for arithmetic expression 1, and that will be that. And let's go ahead and define some other arithmetic expressions. How about if we define A2 to be AX dot ap2, because we're going to build another application expression. How about binop.mul this time, our binary multiplication operator. Oops, I forgot my colon equals there. And now we need 2 smaller expressions. How about A1 and A1? Or A1 and L5? Those are both arithmetic expressions. So here, in the case of A1, we're building an addition expression out of 2 smaller literal expressions. Here we're building a multiplication expression out of an addition expression, this one, and another literal expression. And let's define one more. We'll call A3 binop.add. Okay. A2, the expression we just defined, and how about A1? I forgot my constructor name. That needs to go in front. I should have let you figure that out. Okay, so there we have some expressions. And now as an exercise that I'm going to leave to you, draw an expression tree for L3. So I'll label that as an exercise. Okay, why don't you stop the video now and go ahead and do that. So here we are, back and ready to go. So you can see that we have a really beautiful, simple syntax for an infinitely large set of arithmetic expressions. I'm going to take all of this commentary out and move this over into the test file. Okay, so we can clean up what we have here. And I'll move this comment out and put it over here. And I will remove this comment and just put this stuff together like that. Remove some space here, some space here. Look at it. There it is. It's so simple. These concepts, this concept of inductive definitions really is at the very heart of much of what we do in computer science. Because in computer science, we deal with formal languages, languages that have mathematically defined syntax, where the definition, the syntax definition, specifies the set of permitted or constructible terms in a given language. So look, I mean, there are lots of terms that we can't build in this language. So let's try. Let's define, bad term to be, I don't know, how about binup.add, binup.add? You can't do it, right? Binup.add, the binup. Sorry, I want to build an arithmetic expression, right? Like this. I want to build an arithmetic expression, plus followed by plus. It just doesn't work. You get a type error, right? You can't build syntactically incorrect expressions. They'll be rejected by the type checker. Okay? The only terms that you can build without a type error are those that are permitted by the syntax. And the syntax is really captured by this definition of a set of expression trees, where an expression tree is either a literal, containing a natural number as its contents, a variable expression containing a variable object as its contents, or an application to expression containing a binary operator and two subtrees, left and right, as its contents. That's it. That gives you the ability, however, to build arbitrarily large and complex arithmetic expressions involving addition and multiplication of smaller expressions, ultimately reducing down to, ultimately terminating in literal or variable expressions, because they have no subtrees. So the termination ends with literal or variable expressions. Those are the base cases for the syntax, whereas app2 is a recursive or inductive case because app2 takes two smaller trees of the same kind that are now being composed into a larger tree. Okay, so that's the syntax. In fact, we can take this entire piece of content so far that we've defined, this set of definitions, and say that this defines the syntax of our language. And now we want to define the semantics. In fact, this little piece of code here is part of the semantics, isn't that right? Because it explains what we mean in the domain of arithmetic by our binary operators. I'm actually going to cut that from the syntax piece of code and put that down here in the part of the code that represents the semantics of our expression language. So now look, it's just magical. I mean, how many lines of code do we have here? Essentially, other than these 5, for defining, a set of 4 variables, we have 1, 2, 3, 4, 5, 6, 7 lines of code. It's great. It's so expressive, and it's so clear, and it's so beautiful and concise. And this is the power of inductive definitions. You can define really very complex, interesting data types very easily using these notions of inductive definitions. Okay, so there's the entire syntax of our language right there. As for the semantics, we need to give an interpretation for every term in our language, for every term in our language. Now, this interpretation function here doesn't map terms. It doesn't map expressions to meanings. It just maps these binary operator objects to functions, but we need this interpretation in order to define our larger semantics. So now let's write our evaluator, a function that takes any expression in our language and that returns the number that it means. So this evaluation function will define an interpretation for every expression in our language, of which there's an infinite number. And of course, just as our inductive type definition gives rise to an infinite set of expression trees, our recursive function will be able to take any expression tree, no matter how big, and decompose it into smaller and smaller and smaller expression trees, eventually evaluate the objects at the leaves, which are literal or variable expressions, and then combine the results back up the tree to produce an answer for any given expression tree in our language. And so let's write our evaluation function. Here it is. How's it going to work? Let's call it eval. What will it take as its arguments? Well, first, obviously, it's going to take an expression tree, so let's call that E of type AEXP. Let's actually write it this way. It's going to take an expression tree, let's call that AEXP, as its first argument. And that we don't need anything else to evaluate a literal expression, because if we have a literal expression, it's AEXP.lit applied to some natural number, so we just return that natural number. But if we're given a variable expression that contains a variable object, we need an interpretation to get the value of that variable. And this idea is what we spent a lot of time on 2 lectures ago. So if you're not sure, if you don't remember how we did this, go back and look at what we did 2 lectures ago. The idea, again, is that we're going to take a term in our language and we're going to take an interpretation for the variables, which is a function that takes a variable and reduces it to a value. Okay, what kind of value will variable expressions in our language mean? Well, they'll mean natural numbers. Okay, so we need an interpretation that for any given variable will tell us the natural number that variable represents under that interpretation. And an example of such an interpretation is right here, the interpretation that assigns 0 as the value of every variable. So our evaluator will take an arithmetic expression, an interpretation for the values of the variables, and that's it. That's all we need to do an evaluation of a big old expression tree. And at the end of the day, everything will reduce down to a natural number, which is the meaning of that expression tree. So that's the type then of our evaluation function. From AEXP to var to nat, a function type, to nat, given an arithmetic expression and an interpretation function for looking up the values of the variables in that expression. Given those 2 arguments, we can reduce any expression to the natural number that it means. Okay, and we're just going to define this function by cases as usual. So we'll do one case at a time, and we'll come over here and have some tests for our eval function. Okay, awesome. So the first case will be the case where we're given a literal value. So in that case, the arithmetic expression that we're given will be of the form AEXP.lit applied to some natural number. And here we give a name to that natural number, and let's just call it n. So that's the first argument to eval, is an arithmetic expression. And here we're looking at the first possible case. It will be a literal expression. So that takes care of this argument. The second argument to eval will be an interpretation, a function from variables to nats. And we can call that just I here. Okay. Now, given an arithmetic literal expression that contains a natural number n as its contents, and in interpretation I, we want to return the natural number value of that expression. What should we return? Just return the n. Okay, a literal expression is like a box with a natural number in it. You open up the box, that's what this pattern matching here does. It says, okay, this term that's a literal expression was built in this form, ax.lit applied to some natural number n, to which we give a name here, and we just want to return the number that's inside the box. That's it. Okay, so now let's see if our definition works for literal expressions. You can see that there are various cases that we haven't defined, so we have a non-exhaustive match here. We need to define more cases, but I think that we should be able to apply our evaluation function. So we'll use leans #eval command to apply our eval function to some literal expression, let's say L6, and we also need to give an interpretation here, and so we called the only interpretation that we've defined so far interp0. That will be the second argument to our eval function. No errors. And what is the value to which L6 should evaluate under this interpretation? The interpretation doesn't even matter here, right? We're not evaluating a variable expression. It's a literal expression. So it should just evaluate to 6, and there it is. Okay. And we should be able to do the same thing for our second literal expression, which we called L5. And that expression evaluates to 5. Okay. So we have an evaluator now that can evaluate any literal expression. That is pretty cool. Okay, here's a variable expression x. Let's write a test case for this before we actually write the actual evaluation function code. So let's eval the application of our eval function to the variable expression x under this interpretation interp0. Get an error message. Trying to evaluate sorry. Why? What answer do we expect? Well, we expect that the variable x is bound to 0, or is interpreted as meaning 0 under this interpretation. So we can say here we expect the answer to be 0. But we're getting this error message that says we're trying to evaluate sorry. Oh, yes, you see the problem. We haven't defined how to evaluate variable expressions yet. So let's do that now. ax.var applied to some variable value. Let's just call it v, and some interpretation I. Okay, good. So if we want to evaluate this expression in which eval is applied to an arithmetic expression, here a variable expression, given an interpretation where the arithmetic expression is this variable expression, what is x? X is ax.var, var.v0. Okay. So v here is var.v0. If you don't understand that, stop here and go make sure you see why v here, if we're evaluating this expression x, is v0. Okay, and I is bound to interp0. What value should we expect? We expect to return 0. How do we compute that value? We apply the given interpretation I. If we apply it to x, we get a type error, right? Because I does not apply to objects of type Well, x isn't even defined in this file. It's only defined over in our test file. But if this were an arithmetic expression here, we'd get an error because I doesn't apply to arithmetic expressions. It applies to variables. So we apply I to v, and that gives us our answer. And now, aha, okay, under this interpretation, this variable expression evaluates to 0. Let's try defining a different interpretation of our variables. And we'll define an interpretation where if the variable that you're given is, we'll call this x1, if the variable you're given is x, we'll return 1, otherwise will return 0. So this is a different interpretation under which, I guess we need to say, whoops, aha, I put x here. That's an error. It's not x, it's v0, right? And it's var.v0. Aha, okay, there we go. If the variable we're given is var.v0, we can't use x because that's an arithmetic expression. What we need here is a variable object. So it's var.v0, which happens to be the variable that's contained within the variable expression x. Okay. We break the variable expression x into ax.var v0 because that's how x is defined. And our interpretations map variable objects to values. Good. So under this new interpretation, if we evaluate x under interp x1, we would expect the answer not to be 0 but to be 1, and in fact it is 1. Yet if we evaluated the variable expression y under this interpretation, well, we expect that to be 0, and sure enough, it is. Okay. So we've really got most of our semantic evaluation function taken care of right here. And the only remaining possibility is that an arithmetic expression was built using one of these binary operators. So let's think about how we would evaluate this case. Now let's just write it from scratch. Okay. In this case, ax dot app2 is applied to 1, 2, 3 arguments, an operator argument, a left subtree, and a right subtree. Okay, and I'm going to just call these O, L, and R, just to keep the code short. Okay, and we need to return something. And we've already seen how to do this. What we want to do is we want to evaluate the left subtree to produce a number, a natural number. Evaluate the right subtree to produce a number. Evaluate the binary operator to return a function that we use to combine these two values. And that's how we do it. So we want really, the answer is going to have 3 expressions. Okay, and I'm going to put these on separate lines like this. And so here we want to, get the right function. Here we want to get the answer for the left subtree, the value of left subtree. And here we want to get the value of the right subtree. And that's all there is to it. So we're given this binary operator O. We want to get the right math function corresponding to that operator. So to do that, we apply binop interp to O. Okay. Now, how do we get an answer? How do we reduce the left subtree, which has to exist because the only way to build an app2 expression is to apply it to 3 arguments, right? An operator and 2 subtrees, left and right. So we know we have a left subtree. How do we evaluate? How do we figure out what the value of that tree is? And the answer is we use recursion, right? We evaluate the left subtree, that's a smaller arithmetic expression, under an interpretation. Aha! What interpretation are we going to use? We forgot to specify a second argument to eval. Eval takes 2 arguments, an expression and an interpretation. We left that out. So now we have a name for the interpretation. We want to evaluate the left subtree under exactly the same interpretation we're using to evaluate the overall tree. Because again, we don't want the values of variables to change in the middle of evaluating an expression. That makes no sense. Okay, and we evaluate the right subtree recursively in exactly the same way, under exactly the same interpretation. And that is all there is to it. Look at that. It's amazing. This is an evaluator for arbitrary arithmetic trees. So do we have some? We do. We have some arithmetic tree expressions here. Okay, so let's take these down here. We'll put them in comments, and we'll look to see what we expect to get when we evaluate these binary operator expressions. Okay, if we evaluate A1, what do we expect to get? Well, that's the addition of L5 and L6. L6 evaluates to 6, L5 evaluates to 5. Binop.add evaluates to nat.add. When we apply nat.add to 6 and 5, we expect 11. So for A1, we expect 11. Good. Now, for A2, what do we expect? Well, we are applying binop.mul to A1 and L5. A1 evaluates, well, we think A1 evaluates to 11. Binop.mul evaluates to nat.mul, the natural number multiplication function. And L5, as we've seen already, evaluates to 5. So 11 times 5, this should evaluate to 55. So we expect 55 here. And for A3, we have an arithmetic expression in which we add A2, which is 55, and A1, which we expect to be 11. So for this, we expect the sum of 55 and 11, which is 66. And let's see what we get. Wait a second. Let's see. Are we going to get these values? Well, let's find out. Let's evaluate A1 under which interpretation? Under which interpretation? Well, what's the expression A1? Oh, that's just the addition of 2 literals, okay, 6 and 5. So it doesn't matter what interpretation we use because there's no variable expressions in there. So we want to apply our evaluation operator to the expression A1 under this interpretation, which shouldn't matter because there's no variable expressions in A1. It's the sum of 2 literals, L6 and L5. We should get 11. Aha, okay, awesome. Okay. So now let's eval the application of our semantic evaluation function to A2 under that same interpretation. What's at A2? Oh, well, it's just A1, which we already have a value for 11, times L5. That's a literal. So again, there's no variable expressions in this, so it doesn't matter what interpretation we use here. And it evaluates to 55, as we expected. Okay, and let's evaluate the application of our semantic evaluator to A3 under, again, interp 0 because the interpretation doesn't matter, and we should get 66, and there it is. Okay, now let's see if adding variable expressions to our expressions and evaluating the resulting expressions works. So let's define a arithmetic expression 4 to be, how about x? Well, we want binup. Let's do binup.add. So we will add x and a3. What's wrong with this expression? No, it's not an arithmetic expression. To build an arithmetic expression, I need ax.app2. ax.app2 there. An application expression in which a binary operator is applied to two smaller arithmetic expressions. So here's a variable expression x, and here's a arithmetic expression without any variables in it, a3. We already know that a3 evaluates to 66. What does x evaluate to? Well, that's a trick question, of course, because it depends on the interpretation that we use. So if we evaluate a4 under interp 0, what do we expect the answer to be? This is an interpretation in which x, y, z, and w all evaluate to 0. So we expect the answer 4 to be the same as a3, which is just 66. And sure enough, it is. But if we evaluate that very same expression, x plus a3, in a different state, a state in which x now equals 1, then we'd expect this expression to evaluate to 67. And look at that, it really does. Okay, so this is how you define both the syntax and the semantics for a formal language in which you have literal, variable, and operator expressions. The syntax is defined by ultimately an inductive data type whose constructors, lit, var, and app2 here, tell you how you can build expressions in that language, and where an evaluation function takes an expression and an interpretation that gives a meaning to each variable in an expression, and that recursively evaluates the given expression under that given interpretation to produce a final answer or result or meaning, to assign a meaning to the given expression under the given interpretation. Okay, so the idea that an expression that includes variables can be given a meaning as long as you provide an interpretation for those variables, that's really cool. And that's really, really important. And it's at the very heart of the next formal language that we're going to define in this class. And that will be an even simpler language of Boolean expressions. And this language is going to look very, very, very much like the one we just defined, but instead of natural number operations like addition and multiplication, we'll have Boolean operations like and or and not. And instead of the semantic domain being natural number arithmetic, including natural numbers and functions that operate on natural numbers, the domain of discourse will be that of Boolean values and Boolean operators like and or and not, with which you should already have some familiarity from your earlier courses in computer science. Good.